Okay, all right. Welcome everybody to the educational tutorial on machine learning driven many core systems design and optimization. And the presenters today are Biresh Kumar, who is an NSF Computing Innovation Postdoctoral Fellow at Duke University, and myself. My name is Jana Doppa, and I'm a faculty member in the School of ECS at Washington State University. So yeah, so the outline of the tutorial has two parts. We are going to give you a background on many core systems, why they are needed, what are the key challenges in designing and optimizing them, to lay the land in terms of the problem landscape. And then we are going to talk about machine learning for many core design optimization. And we don't assume any background on machine learning, so we'll cover quite a bit of background on machine learning 101. And then we talk about how we can use machine learning to solve some of the problems that were laid out in the part one. So the part one would be presented by Biresh, and part two I will present. So without further ado, Biresh, you can take over.
Yeah, thank you, Professor Jana. So hello, everyone. So I'll be presenting the first part, which introduces the Manycore system, what are the challenges and why we need machine learning. And then Professor Jana will be discussing the machine learning part. So before we get started, let's look at the journey of computers. So the first computers was like long back in 1946. The ENIAC was one of the first computers we used, but if you recall, or if you have studied, it was huge. Like it used up around 1,800 square feet and weighed 30 tons, 160 kilowatt of power. So as you can see, this is a massive computer. So we started from here, and then eventually we improved. So this is the Apollo guidance computer from 1960s. If you recall, Apollo guidance computer was used in the space missions by the US. So here we had like 32 kilobytes of RAM. The clock speed was just 2 megahertz, not gigahertz, 2 megahertz. And as you can see, it weighs 32 kilo, which is an improvement over ENIAC, but still quite heavy compared to today's computers, and consumed 55 watts of power, which is also very high compared to modern computers. So starting from there, we have reached today where we have computers in many different forms and in many different applications. So today computers come in all shapes and sizes. We have massive computers which are used in data centers. We have intermediate size computers which are used in PCs like desktop and laptop. We also have miniature computers in smartphones and very small ones in like wearables and other places. So we have like all sorts of computers nowadays. And the modern computers, depending on where we are using, can run up to 4 gigahertz of clock, and it can burn as little as 1 watt of power. So if you recall, the Apollo computer was 55 watts. So we have improved quite a lot. And also computers today weigh significantly less than the previous computers. And following this trend, we predict that in the future, we will have even more powerful computers. So we can have like desktop-like computing capability on the smartphones, or if we are a bit more ambitious, maybe data center-like computing capability on the smartphone. So in future, we can expect that our processors can achieve several teraflops per second, and also ultra low power, very reliable and secure. So this is what the future may look like for computing. And one of the reasons that computers have improved steadily over the years is the Moore's law. So Moore's law states that the number of transistors on a chip doubles every 2 years. And as you can see here, starting from 1970 up until 2020, it has stayed fairly true. So the number of transistors has nearly doubled, and you can see it's almost a straight line. So this shows that the Moore's law is still going. And one of the main reasons for Moore's law was the process technology scaling. So here is an example from Intel's tick-tock model. So Intel's tick meant a shrink of process technology, and a tock meant a microarchitecture change. So during the initial phase of hardware design, it was easier to shrink the process technology node. So if you see on the left, For the 65 nanometer, we had a tick, which means we had the new technology, and then a talk, which means we developed a new microarchitecture. And then it was alternate tick and talk for different nodes like 65 nanometer, 45, 32. But as we go into the future and the process becomes smaller and smaller, it's no longer as easy to scale down the process node. There are many challenges. So now we are using 7 nano. Maybe in future we can go even lower, but it's slower than what we were used to earlier. So if you notice in the modern architecture, it's not tick-tock anymore, it's tick-tock, refresh, tick-tock, optimization. So essentially now we are not able to reduce or shrink the process node as easily as before. But still Moore's law is going on, but there are signs that it's slowing down. So we cannot simply rely on the scaling down of process node. We need to come up with new innovations in hardware designs to sustain this rate of growth. And the time for single core processors is almost gone. So nowadays we do not design one super complex core, because designing a fast single core processor has become very challenging because of two reasons. First, the frequency wall, and the other we call power wall. So what is the frequency wall? So typically you can get faster processors by increasing the frequency. So if my CPU is running at twice the clock, the performance you can expect to be 2 times better than last time. But unfortunately, you cannot increase the frequency forever, because even if I can produce a 10 gigahertz clock, my design should be able to withstand and work at that frequency. So it doesn't make sense if your processor doesn't work, but you have a fast clock. But unfortunately, our designs are not able to withstand or work at very high frequencies. So we have hit a frequency wall. And this is also related to the second problem of a power wall. So power is proportional to frequency. So if you keep increasing the frequency, the power also goes up. But we are trying to also shrink the die. So we have a very small area, but we are burning more power. So the power density in current architectures is also very high. So if we increase the frequency any further, we will end up burning our own chip, which is also not something we want to do. So we have also hit what is called a power wall. And there are also applications like in mobile and wearables where we don't want high power, because let's say if I'm making a call on my cell phone and it gets super hot, then it could burn the skin, which is something we don't want. So we are not designing massively powerful single core processors anymore. There has been a shift towards many core design. So if you look at this graph, it's slightly old data, but this shows the trend towards many core. So as you can see, the red line here, the number of transistors is increasing constantly, which is the Moore's law. But unfortunately, if you see, the single thread performance has kind of saturated. So why? Because again, we could get better performance by increasing the frequency, but the frequency has hit a wall. So as you can see, the frequency is not increasing as much as earlier, and it has kind of flatlined. Same with power. So we cannot keep increasing the power like before because the frequency has stopped increasing. The power also has kind of flatlined. So this is what I meant by the frequency and power wall. And because we are not able to increase the frequency, our performance has also kind of saturated. So if you look at the single thread performance, it has kind of flatlined. But around the same time, if you notice, the number of cores has started to gone up. So now we are not designing one super complex core, but many simple cores. So there has been a shift from single core design towards many core design. We want to design many core architectures where each core is simple, not too complex, which is why most modern architectures use the many core design. So what is a many core processor? So many core processor simply means there are many cores. Like in this case, it could be a CPU core or a GPU core, maybe a PGA. So any architecture which has many instances of a CPU or GPU is a many core processor. For instance, in this figure, you see a cartoon diagram which has 81 CPU cores. So such an architecture will be called a many core processor. And this kind of architecture is also quite popular in industry. We have like many such architectures like the Intel Xeon, Tilera, True North, etc. So there are many core architectures in today in the market. And just a distinction, we also use the term multi-core and many-core. Typically, we use the term multi-core for architectures which have less than 10 cores, and any architecture which has more than 10 cores is called a many-core. For instance, the Intel i7 architecture has 6 cores, so we will call this a multi-core. But the Intel Xeon architecture has 28 cores, so we will call this a many-core. So this is just a naming convention, but in both cases, you can see that we are not using a single core anymore. There is a move towards using many cores, not one core. And a few examples of real-world many-core architectures. I think the most popular one would be the Apple M1 chip. So Apple recently released their M1 chip, which has 8 CPU cores. So technically it's multi-core, but it has many cores. So there are 8 CPU cores in the Apple M1 chip. And also the Intel Xeon architectures, which can have up to 28 cores. So we have, you can see on the right, we have 28 cores, 22 cores. So these are some examples of real world many core CPU, but you could also have many core GPU. For instance, the NVIDIA's V100, the Volta architecture has 80 SMs. So you can think of the SM as a simple core. So the Tesla V100 GPU has 80 cores. So as you can see, there are many core architectures out in the market. And many core has 2 types again. So if you take a look at this figure, all our cores are of the same type. Every core is a CPU, and we repeat this architecture many times. So this kind of an architecture where all my cores are the same is called a homogeneous architecture. So we have all CPUs here, but again, no one said that it has to be all same. We could come up with an architecture where we have a mix of cores. So we could have a many core architecture where we have, let's say, some CPU, some GPU, some neural processing unit, some cache, some custom accelerator, and FPGA. So this kind of an architecture is called a heterogeneous many core. We could also have heterogeneity not only in the cores, but also in the communication infrastructure. So typically each core is connected using metal wires, but you could also be more creative and use like vertical interconnect, wireless, optical. So we could also have heterogeneity in communication, and heterogeneous many core architectures are also very common in the market. 2 real world examples of heterogeneous many core. One is the Qualcomm Snapdragon, which is very common in smartphones. As you can see here, the Qualcomm Snapdragon has 2 types of CPUs. So even if these are CPUs, these are 2 different types of CPUs. So it's a heterogeneous architecture. On top of that, the Snapdragon uses GPUs and other units. Same for Apple M1. So the Apple M1 has 8 CPUs, but of 2 types. So it has 4 performance cores and 4 efficiency cores, plus 8 GPUs, plus 16 core neural engine. So as you can see on the same die, I have many different architectures. And so these architectures are heterogeneous many cores. So as you can see, heterogeneous many cores are also there on the market. And there is a trend towards designing heterogeneous many cores as well, because we can now have specialists. So we could have architectures which specialize in some workload versus the other. And typically they work better in practice. And here is an example of a many core architecture which I use for my own research. So at Duke, we have the Intel Xeon Gold architecture, which has 10 CPUs. So we have 4 of these CPUs. So in total, we have a 40 core system. So as you can see, this is just a screenshot after doing an HTOP. So if you use Linux on your machine, you can find out how many CPUs you have by doing an HTOP or a LSCPU. If you are using Windows, you could just open the task manager and take a look. So you could check now how many processors you have on your machine. So far we have seen that there are many core architectures in the market, and there is a shift towards designing many core architectures, particularly heterogeneous many core. But what are the design challenges in heterogeneous many core, and why machine learning? So the first challenge of a Manycore architecture comes from the software. So if I have, let's say, 10 cores, so and I want to use all 10 cores. So it doesn't make sense if I use the software which runs on just one core. So the first challenge is my software should be able or capable of utilizing all my 10 cores. But unfortunately, that's not true. There are many applications, many software which are very unfriendly towards many core design. For instance, in many applications, we have atomic operations, we have IO operations, and these are very unfriendly towards parallelization. So think about it. Let's say you have 10 cores, you have a parallel program, but all the 10 cores are waiting to read some file from the hard disk, but you only have one hard disk. So at any point of time, only one core can read the data from the hard disk. So even though you have 10 CPUs, they have to work sequentially. So even if you can write the code in parallel, but they will execute in sequentially. So these kind of softwares, which are heavily dependent on atomic operation or IO operations, are very unfriendly towards parallelization, and they do not utilize the Manycore as much. Also, even if there is no IO or atomic operations, the amount of speed up saturates after some time. Why? Because after a certain point, other factors like temperature and communication come into the picture, and the amount of speed up flatlines after some point. So we do not see a lot of benefit by increasing the number of cores constantly. Another big challenge in many core design is communication. So we have many cores, but the cores need to communicate among themselves. And in earlier architectures, when we had like 2 cores or 4 cores, we used a bus. So a bus is essentially a shared communication medium, and every core was connected to this bus. So if, let's say, core 1 wants to communicate with core 2, it will send the signal on the bus and core 2 will listen to the signal. But one weakness of the bus architecture is that we cannot do parallel communication. So we cannot have 2 cores communicating at the same time, because then the signals would interfere. And this is a big problem in Manycore, because when I have, let's say, 64 core, there is a very high chance that two or more cores have to communicate at the same time. One good example would be, let's say there are 2 users using this system and both of them are playing some game. And games tend to be very communication intensive. They need to fetch data from the DRAM constantly. So now if I have 2 cores which are running some game, and in both cases, both of them are trying to fetch data from the DRAM, but unfortunately, due to the bus architecture, you can have only one core communicating while the other has to stop. So you would see a lag in performance, your game will hang in the middle, and you would not be happy. So communication is a big problem in many core systems, and we will spend a lot of time on this topic later. So communication is another challenge. The third big challenge, I would say, in many core is the memory. Let's say you have a single core which is running some workload and it demands 1 Gbps of data for processing, and you have your DRAM which can supply also 1 Gbps. So supply equals demand, everyone's happy, we can get the best performance. But what happens if you increase the number of cores but you forget to improve your memory? Now let's say you buy a 3-core system and you parallelized your application, and your application doesn't have a lot of atomic operations or IO, but now all your 3 cores are demanding 1 Gbps of data. But since you forgot to improve your memory, it's still going to supply 1 Gbps of data. So your supply is lower, but the demand is higher. And now what will happen is you will see no gain in performance. So your performance will remain as it is, or it could get even worse. So you increase the number of cores in order to get better performance, but you may end up with even worse performance. So memory bottleneck or memory bandwidth bottleneck is a big problem that is being looked into. Another challenge comes from the manufacturing. So when we manufacture, silicon wafer die often has a few defects. Now, if I am making very small chips, let's say I make a single core architecture, in which case I can make a lot of cores, and then I will simply discard the cores which are defective. So my yield is quite high. So small architectures tend to have a better yield. But when I'm making many core architectures, they tend to be bigger because of course we have 10 cores versus one core. So now we can make fewer architectures. And now if I discard the defective chips, my yield goes down. So as you can see, my yield for making many core systems is also low. So I can sell less product and the profit would be lower. So manufacturing is also one of the big challenges in Manycore. So far we have talked about some of the challenges. Again, these are some of the challenges, not all the challenges, but you can see that Manycore design is not free. There are many issues that need to be solved. So why machine learning? We already saw that many core architectures exist and you can buy it in the market. So why do we want to use machine learning suddenly? So the reason why we need machine learning for future designs is because our designs are getting more and more complex. So today we have architectures which are maybe 10 core, 20 core, maybe 40 core, but who knows, in future we could be having like 100 core design or more than 100 core design. In that case, the design becomes more complex. So bigger the system size, more designs you need to explore, and it just becomes too hard when you have so many options to explore. Also, another challenge comes from the use of heterogeneity. So as we saw in the Apple M1, you have a mix of cores. So there is also a shift towards having this kind of a heterogeneous architecture with components which specialize in one subtask. And designing these architectures are quite difficult because now you have to design with everyone in mind. So you have to design so that the CPU gets the best performance, the GPU also gets the best, the FPGA also gets the best. So now the design just becomes even more complex. And also another big reason for the difficulty is the domain. So where are we using the computers? So now we are using computers almost everywhere. But unfortunately, every domain has its own requirement. There is no one size fits all design anymore. For instance, let's say if I'm designing a chip for cloud computing, let's say I will design something that has the best performance. But maybe that chip is not suitable for automobile, let's say, because in self-driving car, yes, performance is important, but probably reliability is even more important because anything goes wrong in self-driving car would have more catastrophic consequences than the cloud. So reliability is more important. So you can't use the same chip you used in cloud in the automobile. You need to design again. And so a combination of all these factors is making our hardware design more complex. And the existing methods do not scale well when the designs become more complex. And here is where machine learning comes into the picture. It allows us to rethink and redesign our design algorithms to get better hardware in less amount of time. And not only is our hardware getting bigger and more complex, our software is also getting bigger and more complex. So now we have big data applications like machine learning, bioinformatics, graph analytics, which have become very, very important. And these often work with like terabytes of data. And now if we run this on our existing hardware, it takes a lot of time. And so we end up paying a lot of money for the energy and other costs. So this is not very efficient. And there is a need to also develop more optimized and better architectures for the application. For instance, the cost to run the GPT-3 machine learning model is estimated to be somewhere between $100K to $150K, which is quite high. So if we want to run these massive workloads in the future, we also need to come up with better designs. Hence, we need to rethink our design strategy, and machine learning is a key tool in this endeavor. And to give you an idea of how important machine learning has become in hardware design, so I looked up and I found the research papers that were published in a conference called Design Automation Conference, or DAC. So DAC is one of the popular conferences of hardware design. But in 2019, I found that almost 20 to 25% of the accepted papers had something to do with machine learning. So think about it. This is a hardware design conference, but 25% or 1/4 of all the accepted papers had something to do with machine learning. So this kind of gives you a sense that machine learning is very important for hardware design, at least in academia. And not only DAC, this trend is true for other hardware design venues as well. For instance, even I am presenting a machine learning paper in ESWEEK on Wednesday on hardware design. So it's become very popular in hardware design, not only in academia, but also in the industry. So I pulled this data from LinkedIn, and this just shows how the number of jobs that need machine learning is growing year after year. And if you look at the third entry from the top, which is hardware and networking, you can see the number of jobs in the industry for hardware design is also growing year after year. So this is slightly old data, but this gives you the idea that machine learning for hardware design has also picked up like prominence in the industry. So machine learning has become an important part of hardware design, both in academia and in industry. So with this knowledge, what can we do? How can we use machine learning in hardware design? So how can we use that? Of course, we can use machine learning in many variety of ways for variety of design problems, including, let's say, in the design, like place and route for testing. So you could reduce the time it takes to test massive chips using machine learning, hardware security, which is becoming a very important problem, and also optimization. So there are many ways we can use machine learning in hardware design. So with that in mind, I would next like to talk about two particular problems that arise in Manycore. And these are just examples. There are many, not two, there are probably 200 design problems in Manycore design, but we'll focus on two examples, and then Professor Jana will discuss how machine learning can solve these problems. So let's start with a problem called task mapping. So first of all, let's say I want to do a very simple task. I have two vectors, A and B, and I want to add A plus B to get the C. Now, typically, if I have to write a C code for a single core, I would just write int main and then run a for loop and add it. So C of I is A of I plus B of I, and we can do the vector addition. But a sequential method will take n cycles. So if I have to do n additions, it will take n units of time, right? But if I have a parallel processing, if I have many core, I'll modify my code such that each thread now does one or a handful of additions. So instead of one core doing n additions, I will now divide my work on multiple threads, which will run on multiple cores. And let's say if I have n threads, each thread is doing one addition. Now I can finish all my additions in, let's say, one cycle, which is, as you can see, much faster, n times faster. So there is benefit in having a parallel computing. So what is the problem of task mapping? So the problem of task mapping is I have n threads, I have n cores. Now which thread should be run on which core? So that's the simple problem of task mapping. How should I map these threads to my existing cores? Now, why would I want to do that? Well, task mapping, even though it looks simple, it has very big impact on the performance. So depending on how you map your threads, we can get very different execution time. We could also improve our communication, power, temperature, and a lot of design issues. So let's look at some examples why task mapping is so important. So let's say I have a workload where every time I see a non-zero, I will print out hello world, let's say. And let's say I've given a 2D array, and the way I have written my code, I will generate a thread to process each row. So I have 4 rows. So I generated 4 threads, and each thread is reading 1 row. Now, if you notice, the rows 1, 2, and 3 just have 1 non-zero. So you're going to do 1 hello world. But the 4th thread has 6 non-zeros. So it's going to do 6 times the amount of work the other thread does. Now, if you just naively map all these 4 threads on your 4 cores, you will end up with a situation where your first 3 threads are done within 1 unit of time, but your last thread is continuing to work for longer for 6 units of time. Now, this is a waste of resources, right? Because I have a 4-core system. 3 of my cores are not doing anything for 80% of the time, whereas one core is doing most of the work. Now, this is very inefficient because I have a many-core architecture, but I'm not utilizing it fully. Here is how task mapping could solve this problem. So this is our baseline. This is the naive mapping where I just mapped it randomly. So I'm using 4 cores, and the total time it takes to finish this task is 6 units of time. But what if I mapped the first 3 tasks on one core and the 4th task on the other core? So now I am using just 2 cores, and it still takes 6 units of time, but I'm using 2 cores, which is much better than my first case where I was using 4 cores and taking 6 units of time. So even though my performance is constant, I am using fewer cores. So now I could use the rest of remaining 2 empty cores to do some other task. Again, we could also do another way of task mapping. What if I split my 4th task into 2 subtasks? Now I could do my first 3 tasks on one core, and the 4th task I split in 2 and do it in 2 other cores. So in this time you need 3 cores, but you reduced your execution time to 3. So you can see 2x improvement in performance, but you're using 3 cores. But if you compare case 3 with the case 1, which is your baseline, you can see that it's better than case 1 in every way. You're using fewer cores and your execution time is 2 times lower. So this is what task mapping can do. If you can find this optimum task mapping, not only will you use fewer resources, but you can finish your work much faster. Another reason why we may want to do task mapping is temperature. Let's say you have a 4-core system and you're doing an assignment or a for some homework, maybe where you have to train a machine learning model for 1 hour. So you ran a machine learning task and it's running on some core, let's say, but because it's going to run for 1 hour, you have nothing to do and you started playing a game. But your game is also mapped to, let's say, a core just next to the machine learning workload. Now, both machine learning and games are very computationally expensive. So what will end up happening is the region around these cores will be super hot, while the region far from this core, closer to the CPU 0 or core 1, will be cooler. Now, this is bad because as soon as your chip becomes too hot, there is a risk that your chip will burn, or you may end up throttling your performance. So you will see a lag in performance in both your machine learning and your game. So because you did an inefficient mapping, you ended up with suboptimal performance, or you may end up damaging your chip. And this problem is not only going to be limited to your CPU, but it could also spread to your neighboring devices. Let's say you have your DRAM stick just next to the core 3. So if you now run 2 heavy workloads on core 2 and 3, that heat could also spread to the DRAM, and DRAMs are very inefficient at high temperature because they leak faster. So because we did an inefficient mapping, my performance gets throttled and also my DRAM gets slower. So this is a problem that you could have solved if you had mapped one of your compute intensive workloads maybe on core 0. So that way you don't end up with a very hot region and you don't experience a performance throttling or affect the DRAM's performance. So this is one way how task mapping could help with temperature. Another example, let's say I have a massive many-core system, and at some point, let's say this is the heat map. So I have a situation where the center of my chip is very hot, but the periphery is not as hot, it's cooler. So now if I have to, let's say, run a game or a machine learning workload, I have a choice to make. I could run my game on the center of the chip. So let's say I pick the core, which is already hot, and I'm running a compute intensive workload on top of that. So again, because that region is already hot and we are running another workload, it's going to end up either throttling your performance or damaging your chip. So if I have knowledge of this information, I could have mapped in the cooler region. So that would allow the hotter regions to get rid of the heat and cool down. So this is how task mapping could influence temperature in a many-core system. Also, task mapping also impacts communication. So if I know that tasks communicate in some way, let's say task 1 communicates with 2 and 4, but not with 3, then if I do the naive mapping as the top one, I end up spending 6 hops or traveling 6 hops to do the same amount of communication. But I could do better if I do the mapping, which is at the lower mapping. So now I'm doing the same amount of communication, but by traveling just 4 hops. So I now improved my time it takes to communicate by 1/3. So task mapping helps in a variety of ways. Now, who would want to do task mapping? So task mapping is important, of course, in every case, but I think it's very important for cloud service providers, because if you think about that example of load balancing, I can do the same amount of task. If I use fewer cores, then as a vendor, I can use the rest of my cores for some another customer. And also as a customer, you don't want to pay a lot of money. So if your work gets done faster, you end up paying less. So task mapping is very important for different like hardware, especially in the cloud setting. And for our particular tutorial today, we'll focus on a sub problem of that. So we are going to look at communication aware mapping. So we saw that mapping helps with a lot of other factors like temperature and other, but we'll focus on the communication aware mapping. So here the idea is that we are given the application's behavior. So it could be in the form of a graph or some heat map. So we know the behavior of our application. We have n tasks. And now the question is, how should I map this n task to the n cores to get the best performance? Or maybe in this case, to reduce communication or reduce the time it needs to do the communication. So first of all, what are these heat maps? So the heat maps essentially is a map of how many times a thread I will communicate with thread J, which you can easily obtain using like simulations. So we could use like Gen 5 or Gen 5 GPU, GPU sim simulators to run some workload and study how many messages are sent between thread I to thread J. And you could use this information to influence the mapping. So here are a few examples from our experiments. For instance, we have run Canil and FFT, and as you can see, both these applications have very different characteristics. So the rows indicate the sender thread and the columns indicate the receiver thread. And as you can see, in Canil, we have very unbalanced traffic. We have some red zones, some blue zones. So blue means very low traffic and red means very high traffic. So the communication in Canil is very different from FFT. So the mapping strategy we will adopt in Canil may not work with FFT. So what if we had this information? Can we use it to do better mapping? And here are a few more examples. So this is a traffic pattern from a CPU GPU based system. So here we saw the traffic pattern is what we call many to few. So we have, if you look at the bottom row, we have the GPUs and the LLC, which are the cache. So we have a lot of GPU to LLC and LLC to GPU communication, but we do not see GPU to GPU or LLC to LLC communication. So we call this pattern as many to few. And we also tested other applications, for instance, in bioinformatics, we tested applications for genetic applications. And as you can see, we ended up with this barcode looking pattern. So if we have knowledge of these traffic patterns, we can take better decisions. For instance, the mapping for this traffic pattern may not work for this barcode looking pattern. So if we have this information, how do we map to reduce our communication time? And how does it impact? So let's take this example. So here, if you notice, we have a few red areas and a few blue areas. Red means high communication. So we have a few threads which receive data from all the other threads. So essentially, you could think of it as this picture. So we have many, let's say, black threads, which are going to send data to this brown thread. Now, how does task mapping influence anything here? So let's say, in my first case, I map this brown thread on the corner of this chip. Now, there are two problems with this approach. First, every data that will reach this brown thread has to use these two links. So we basically have just two ways to reach this thread, which could lead to traffic jam in the NOC. So let's say you want to go to a concert, but there is just one road that goes to the concert. So everyone who has to go to the concert will take that road, and you may end up in a traffic jam. The same thing happens here as well. So if you map the thread at the corner, you only have two ways to reach the thread. So you may end up with a traffic jam. And also, the longest distance that a message has to travel to reach this brown thread is 8 hops. So you could have a thread at the absolute other diagonal corner, and it has to travel 8 hops to reach this other thread, which will also take a lot of time. Now we could solve this problem if we had mapped this brown thread in the center of the chip versus the corner. Why? Because first of all, in the center, you have 4 links. So you have 4 ways to reach the same thread. So now the chances of a traffic jam goes down. And also the longest distance a message has to travel is just 4 hops. So we can improve our communication by simply mapping this brown thread not on the corner, but on the middle. So we can make this kind of decisions by looking at the traffic pattern of the different applications. So this is where task mapping comes into the picture. So again, to summarize, what is the problem of task mapping? So here we have end task and end course. The question is, how should I map this end task to the end course to get best performance? And the problem here is that you can have n factorial different mapping. How do I pick that one best mapping out of n factorial? And if the n factorial is very high, let's say I'm designing a 100 core system. In that case, I have 100 factorial choices, and that is simply an impossible task. So here is where machine learning can help us. And Professor Jana will explain how machine learning can solve this problem and similar other problems. The second problem I'd like to discuss is also similar to task mapping. So this problem arises due to the communication bottleneck. So typically in any architecture, the computation is faster than communication and memory. And as a result, it takes an order of magnitude more time and energy to fetch data from the cache and DRAM than it takes to do the actual computation. And one of the problem is because we are using a bus. So if you recall, in a bus, we cannot have parallel communication because there will be interference. So one has to be stopped while the other communicates. And this is not scalable with system size. So if I have a Manycore system, this will not work. So one of the ways we can solve this problem is with the help of a network on chip. So a network on chip is essentially a network, like it's like the internet. So every core has its own dedicated router. So every time a core wants to communicate with another core, you send the data to your router, and that router then sends the data to the destination router, and then the destination will get the data from the router. So essentially you have like an internet-like infrastructure on the chip, which is why we call it the network on chip. And network on chip is very scalable with the system size and is used in many core design because it gives us high throughput, low latency, better energy efficiency, and it has a lot of benefits. So how does the communication work out in the NOC? So here, as you can see in this figure, we can have many communications happening at the same time, because if you see, CPU 3 is communicating with CPU 5, which is indicated by the red arrow. The CPU 7 can communicate with CPU 1 at the same time using the green arrows. And as you can see, none of the links are common in these two communications. So you can have both the communication happening at the same time. But again, this is not a magical solution, because now if CPU 4 wants to communicate with CPU 5, that will not work because all the links around the router are busy. So even though we can have many parallel communications, it cannot have infinite communication. But this is more scalable than having the bus. Again, a few real world example. So NOC is used for many core design like the Intel Xeon architecture, which uses a mesh NOC. It's also used in the Intel i9 architecture, which uses a ring NOC. So we have different options of designing the NOCs as well. And how do we design NOC? Again, you could design NOC in as many ways as you want. So basically you have some routers, now you need to connect the dots. So how do I connect these routers so that I get a connected system? And you can do that in many ways. So you can make simple architectures like mesh, tree, torus, maybe a star, but you're not limited to just these architectures. You could also come up with random or something semi-random architecture. So in this particular work or this tutorial, we will focus on what's called the small world NOC. So essentially it's a semi-random NOC. As you can see, it's in between a random and a regular NOC, which is why I call it a semi-random NOC. And so we can design as many NOCs as you want, as long as it connects all the cores. A few other examples of NOC includes the smart NOC. So in a smart NOC, the idea is that I could add muxes to bypass some of the routers so that I get a virtually long range link. So the idea was very interesting. So this is one way you could also design your NOC. You could also use different technologies to make your NOC. For instance, I could use a 3D NOC where I stack two different layers and connect them using vertical links, or I could also make an NOC using wireless or photonics. So there are different technologies that are also being studied. These are yet to be adopted by the industry, but these are probably we can probably expect these NOC designs in the future. And our group has worked quite a bit on these different NOC designs. For instance, in the case of wireless, we have found that if you are designing very large chips, wireless is better than wired. So from our experiments, we have found that if the chip dimensions are larger than 7 millimeters, so if you want to have a connection which is longer than 7 millimeter, it's more energy efficient to use a wireless versus a wired link. So we could have like an antenna on the chip, which sends out the data, and a receiver antenna, which receives it. And you could have long distance communication in a single hop. So wireless NOC is also a very like a good option for designing NOC. Also, we have worked on 3D NOC where you stack two layers on top of each other and connect them using metal wires. And 3D NOCs are also very good in terms of performance and energy efficiency. And how does a NOC work? So similar to the rules you follow while driving, NOC also has its rules. So we do not have like a chaotic messages going around everywhere. There are set rules that the messages have to follow in the NOC, which is called the routing protocols. For instance, in the mesh NOC, we follow a XY routing or a YX routing, which is basically just following a Cartesian coordinate. So in XY routing, you go along the X, then along the Y. If you have irregular NOC, we can use the shortest path algorithm. So we can have different routing protocols. One of the common protocols that we see is wormhole routing. So this is used when the messages are very large. So if a message is very large, we break it into smaller pieces called flits. And then each flit is sent in this wormhole routing. So first the header bit goes, then you send the body flits next to it. So it looks like a worm. So if the head of the worm goes a certain way, the body follows, which is why it's called a wormhole routing. And why again should we design better NOCs? Because again, the better NOCs means we can have faster communication, which will lead to better performance because your time to communicate is also going down. And also better NOC designs could lead to better temperature, as we have seen in one of our work. So in one of our work, we have done floor planning plus NOC design at the same time. And we have found out that a better design could end up reducing the temperature for the same workload. So let's say if I have this architecture on the left, so here you can see these red regions, which means high temperature. So there is a chance your chip will burn. But if you design the architecture with thermal in mind, you could end up with the same design or different design, but you don't see these red spots anymore. So a good NOC design with floor planning could also result in lower temperature. Also, better NOC could improve the lifetime of your device. So if, let's say, a few links are being used over and over, there is a very high chance that these links will fail. So real world example, let's say, if everyone uses the same road in the city many, many times, that road will fail faster and will need more maintenance. But there is no maintenance in an NOC because you can't do like repair in the NOC. So here we could solve this problem of aging by using some bypass route. Like let's say the green links are being heavily utilized. What if I add a bypass route? So now some of the messages could take this alternate route, which will ease the pressure on the earlier links. So this could improve the lifetime of my device as well. So we have seen the benefits of NOC design, and similar to the task mapping, we could also formulate the NOC design as a search optimization problem. So again, we'll focus on communication aware design. So given the application's characteristic, which NOC should I pick? I have all these choices like mesh, torus, tree, small word. Which NOC should I pick? Which will work the best for a given application? And here we'll focus on the small world NOC in particular. So again, let's take a look at how NOC design could improve performance or influence my design. So let's take the same workload again. So it's the same workload from task mapping. Again, you can see that we have these strips of red, strips of blue. The red ones are receiving a lot of data. So again, you could think of it as a lot of threads. Let's say the black ones are sending data to the brown thread. Now, again, let's take the earlier example. If I map my brown thread at the corner, there are two issues. First, you only have two ways to reach there. And second, some of the threads have to send, so the messages from these corner threads will have to travel a long distance to reach to that destination. But we can solve this problem by designing a better NOC. Like, what if instead of having just these two links, I add a third link on top? Let's say this red big arrow could be my third link. So I have added a long range link from one corner to the other. So now I have three ways to reach the same thread. So earlier we were solving the same problem by task mapping. This time we are solving the same problem, but with a better NOC. So instead of moving the thread, we added one more link. So we could also add more links. So we could add 4 links to the corner CPU. In this way, we can have 4 ways to reach the corner thread by designing a better NOC. Also, because of this long range shortcut, I have reduced the longest path it will take to reach the brown thread by 5 hops. So we have significantly reduced the distance it requires, and also we have added more paths to reach the busier thread. So NOC design could also solve the same problem. So to summarize, what is the NOC design problem again? So here, again, we have N cores and L links. So the number of links are not the same as the number of cores this time. We have N cores and L links. Now the question is, how should I connect these N cores using these L links so that I get the best performance or maybe power? And again, the problem, we have a similar problem as task mapping. We have N choose L number of possible ways of connecting the cores using the L links. And again, if I have like 100 cores, the number of links are also more than 100, in which case I have, again, a very big design space. And finding that best NOC in this big design space is a problem. So this is a search optimization problem. And existing methods do not scale well in such huge design spaces. And here is where machine learning comes into the picture, and it can solve some of these problems. So far, we have talked about 2 of the challenges for Manycore design in details, but these are just examples. There are probably 200 more challenges, but you kind of get the idea that the NOC design has problems which tend to be large, massive, and many of the existing design methods just do not scale. And here is where machine learning can solve this. And with this, I will hand it over to Professor Jana, who will now discuss how machine learning will solve these problems.
Thank you, Biresh. That was a wonderful presentation for the part 1. And while I'm setting up, sharing my screen, there is a question in the chat by Biswadeep. If you can read and answer, that would be good.
Okay, so I see. So it's, is it necessary to use architectural simulators to find these communication pattern, or is there a method to do this on commodity processors, Xeon, for example, at runtime? Okay, so here from our experience, we found that it's not possible to get it directly from the board. unless you have like a dev board, like if you just buy a commodity board from the market, we typically can't do that. So this information is not available. So which is why we use simulators. And also simulators are more flexible in what kind of designs you want to simulate. So I think the simulator just gives us more flexibility, which is why we use the simulators. Does that answer the question? Oh, thanks.
Okay, all right, good. Okay, so let's start the second part on how to use machine learning for Manycore design optimization. And Biresh has presented some canonical design optimization problems in the context of Manycore, but there are many other design optimization problems you can frame the same way, which they take as, you know, a similar abstraction. Okay, so before we want to learn about how to use machine learning, we need to know about what machine learning is and what kind of tools it provides for us before we tend to use them. Okay, so I don't expect anybody of you to know about machine learning. So I'm going to provide a quick machine learning 101. So machine learning is a branch of engineering that develops technology for automated inference, right? So you want to automate any particular task, you know, in the context of our particular problem space, we want to do design automation. So we want to automate design, right? So it combines four particular technologies. One is probability, statistics, optimization, and computing algorithms. So that's what machine learning is. And if you want to understand a little bit more, I think it's very useful to contrast machine learning with traditional programming. In the traditional programming, before computers were there, you know, if you want to solve a problem, you know, you would take a piece of paper and a pen, and then you would start doing that, right? And that process doesn't scale as you are given more and more problems, right? So what computers allowed us to do is that, well, if I know how to solve the problem as a recipe, right, I would write a program in a high level language, and then a computer would convert that high level language program into a program that it understands in zeros and ones. And I can repeatedly give lots of inputs and have that program execute on that input to produce the output. And as you can see, this is a big, huge leap from manual process, because it scales to any number of inputs, right? So you can solve these problems in parallel. In the other case, you have to have many humans. And the second thing is that it also, unlike humans, a computer won't get tired, right? And it will not lose accuracy as a function of the number of problems it is solving. But the big point here is that still a human needs to write a high level program to do the task. For example, adding two numbers or multiplying two numbers, finding a square root, you know, solving a differential equation, solving an integration, whatever, right? Now, what machine learning does is it takes this automation to the next level, and that's why we call it automating the automation. Right? So in this case, in this paradigm, what we do is we tell the computer we want to solve a particular problem, and for any given input problem, I expect a certain output, right? So you're only specifying the input and the desired output for that particular input, and you give a lots of that, and that's called training data. And that training data is given to a computer, and computer kind of spits out an intelligent program that would hopefully produce your desired outputs on unseen inputs. So that's what machine learning is. Okay. So at this point, you know, you might think that, okay, it's all looks like magic, right? I mean, the better analogy for us to think about is machine learning is more like gardening. So you need seeds, and here the machine learning algorithms are the seeds, and you need nutrients, and the training data is what is the nutrients. And still there needs to be a gardener, which is basically you, who is applying machine learning or using machine learning. And then the plants, as a function of seeds, nutrients, and the gardener, you will have better and better tools or programs that would automate your task, right? So that's a better analogy to think about machine learning. So here is one funny example I would like to talk about. So here, a machine learning professor was probably going to a conference, and he was sitting on Uber, and the Uber driver says this to the machine learning professor. See, when AI comes, I'll be long gone, being replaced by autonomous cars. But the programmers in those companies will be too, by automatic program generators, right? And I could easily generalize this to say, well, we go to DAC or ESWEEK whenever it is in person, and we sit in the Uber, and the Uber driver says, you are designing these electronic design automation tools, and soon you will be replaced by machine learning, right? You can easily kind of talk about that. It's not hard to see. So with that, now we understand the big picture about machine learning. So let's talk about some basic learning paradigms in machine learning. The most basic learning paradigm is what is called supervised learning. And in supervised learning itself, depending on whether you're trying to predict a discrete output or a continuous output, it's called classification or regression. So let's look at a simple example to understand what supervised learning is. Let's say we want to train an image classifier that takes the image of a face of a person and predicts whether the face is of a male or a female. Very simple task, right? So what we would do, we would collect basically lots of images of faces, and we will as a human expert would label them as male or female. And that would be the training data that would be given to the learning algorithm. And then here is our intelligent piece of software that we are trying to kind of create, right? And once this training data is fed to the machine learning algorithm, this program is generated, and you can give new images, and it will basically predict whether the images are of male or female. Okay. So this intelligent program has some unknown variables. Let's call them theta. These are some bunch of real values. And once you give the training data to the machine learning algorithm, the machine learning algorithm would give the right values to those variables so that this program behaves as you want it to. And there are many machine learning algorithms. You can plug in logistic regression, support vector machines, decision trees, and deep neural networks. Similarly, like I mentioned to you, if the output value is continuous, in the previous case, it was discrete and binary, so male versus female. And if I'm trying to recognize images, face recognition, for example, then I would have more than two values, right? So the labels would be the names of people. In the case of regression, the output is a continuous value. So for example, you want to predict stock market price as a function of financial specs, right? So pretty much the same technology, the same story applies to regression as well. The only difference is that the output is continuous. Another paradigm in machine learning is what is called supervised learning, active learning. So the most popular paradigm is supervised learning, but the main drawback of supervised learning is that you require a lot of labeled data to be able to build good classifiers and regressors. And in a lot of real world applications, getting that label data is very, very, very expensive. Okay. And in the context of our design space exploration and optimization, the design simulations that you have to do, which are very expensive, you can't get a whole lot of labeled data as well. Okay. So active learning, what it tries to do is that, so the active learning name actually, it's kind of, to draw a parallel, you have to talk about passive learning. In the passive learning, there are a bunch of problems, and then you randomly sample some problems and produce solutions, and then you give it to the learner. So you don't even think about the learner when you are creating the label data. Whereas what active learning does is, well, here is a teacher, and I'm trying to train this student, which is basically a computer, and I will let the student drive the learning process, right? So the student gets to pick which questions it needs to be answered. So what you do is, this is basically your computer program. It looks at all the unlabeled examples or problems that need to be solved. And based on its current knowledge, it basically selects one input that it thinks that, if I get an answer for this or a label for this, my knowledge will improve the most and I will move closer towards the target concept that I'm trying to learn. Okay. And then it presents that question to the expert or an oracle. So this could be a human or it could be a computationally expensive experiment, right? In the context of design automation problem, pretty much this is basically a computational simulation. And then the teacher or the oracle produces the output, and then the learner updates its knowledge based on the new training example it got, and it repeats the process. And the name of the game is that, if you need n examples to learn a target concept to arbitrary accuracy, um, then you would only require order of log n number of supervised examples in an active learning paradigm. So you can easily see that active learning allows you to learn much more efficiently using less number of labeled examples. In fact, exponentially less number of examples. Okay. Um, Now, before I talk about the next paradigm, I want to contrast with the one-shot decision making with sequential decision making. In one-shot decision making, you basically are making one decision independently. So for example, if you are given an image of a cat or a dog, you pass it to a convolution neural network and you would get the label saying whether it is cat or dog. And if I give you a new input, new image, and then whatever prediction I made for the previous image has nothing to do with my new decision. These are independent things. But then in sequential decision making, right? So for example, you're trying to route data on a network, right? And you will keep doing that over and over again, right? Similarly, if you want to manage voltage and frequency of different cores and the network elements in a Manycore, you have to repeatedly take decisions about what voltage and frequencies you want to apply as a function of the workload. And this is what we call sequential decision making. And the reason why we call it sequential decision making is that the impact of your previous decisions affect your future states and your future decisions. So it's very important to kind of take into account these dependencies. So reinforcement learning is one such paradigm that allows you to, a general framework to allows you to solve these kind of sequential decision making problems. So in the reinforcement learning paradigm, what happens is you have either a physical robot or a software agent put in an environment, right? So for example, here we want to control voltage and frequency of the cores and the network elements, let's say, and we put it on the chip, right? The Manycore chip. And what this agent does is that it senses the state of the environment, and based on the current state and the workload, it will decide what action needs to be taken, right? And if the action taken is good, you would get reward, or if the action taken is bad, the environment will basically give you some penalty. And it's an iterative process that in a sequence of iterations you would take actions, you would get rewards, and you will basically try to update your knowledge. And the overall goal is you want to kind of learn the problem solving behavior or sequential decision making policies that allows you to maximize your cumulative reward over lifetime. So you want to take those actions that will give you very, very high reward in this particular environment. Okay. So with that, that's basically the machine learning 101. You need to know basically supervised learning, active learning, and reinforcement learning. And we are going to talk about how we can use active learning and supervised learning to solve design space exploration and optimization problems in the context of Manycore design. So I'm trying to list down the design optimization problem for the many cores, right? So you have cores, you have routers, and you have some communication links. And we are basically told, the design space is determined based on how many cores are there, how many routers are there, and how many links that we are allowed to place. And then we are also given some physical constraints. For example, when you're designing the network needs to be connected because every core should be able to transfer some data to another core, right? And similarly, there could be other physical constraints that you don't want fat routers, right? So you don't want too many links going out of a router connecting a lots of cores. So otherwise, that would be a performance bottleneck. And we are given a bunch of target applications. So for example, we could talk about deep neural network training as a workload, or some graph analytics as a workload, or some bioinformatics application as a workload. Okay. And then we are asked to find designs that optimize, some design objectives like performance, power, temperature, and so on. Okay. So what we want to do is that we have this huge space of designs, and we want to find the best design. And in this context, it is where to place cores, where to place routers, and where to place the communication links. So let's talk about what the challenges are, which Biresh already mentioned, that the design space is combinatorial, right? So there are many ways to kind of place these cores, routers, and links, and you can think about each design as a graph structured object because the nodes are these cores and the links are these edges. And the design space is large, and it grows as a function of system size. For example, if you are looking at 64 cores versus 1024 cores, the design space grows significantly. Similarly, the design space could also grow, in terms of what integration technology we are using. So for example, if we are using monolithic 3D integration, the cores and the routers can be designed over multiple tiers, right? So that almost exponentially increases the space of designs. And like I mentioned before, the key challenge really is that the design evaluation requires expensive computational simulations. So one thing often people do, to go about this design optimization problems is that there's a lot of knowledge from the hardware designers that they have gained over years, and they use that to design analytical models as a function of the workload, um, to quickly narrow down the design space to the most promising designs. And then only on those narrow promising designs, we perform design optimization using expensive cycle accurate simulations. Okay. So I'm going to quickly talk about an example design space, which Biresh already mentioned, the small world design space. And a quick reminder, a small world is characterized by many short links and a few long range links. Okay. And the main advantage is that it's energy efficient because the average path length is small. And it's also inherently robust because even if few links fail, average path length increases marginally due to link failures, right? So small world has this very nice property of that will allow us to do efficient communication, but it also provides reliability. So if you want to design just an NOC, we basically run the workload, and we get basically how the cores are communicating between each other, right? So this Fij kind of talks about the communication frequency between cores I and j, and Hij stands for the hop count between nodes I and j, which means that how many hops you have to kind of jump before a packet can reach j from I. And Dij is basically the physical distance between nodes I and j, and M is the number of switch stages, right? So this communication cost is basically trying to talk about what is the weighted average hop count for a given network, a communication network, right? So once you have the workload and a particular placement of the links in the course, you can actually have a candidate design, and you can plug it in this particular cost function, and you would get a numerical cost. Now, the only question is that we want to find that design that has the least cost among all possible designs, right? That's the optimization problem. So we can perform, because this is basically a combinatorial search problem, you can use a variety of search algorithms, including simulated annealing, genetic algorithms, and so on, that has been used in the not only in the EDA community, but also other communities, right? But one common drawback, especially when you have a complex design optimization problem and very large design spaces, is that these algorithms do not tend to learn from the designs that are explored in the past to guide the future exploration, right? So whatever you have learned based on your past exploration, you want to put it to use so that you only explore the most promising regions, right? So the key idea, as you might have already figured out, that you want to learn some kind of knowledge from the past search experience, and so that you don't search in unpromising regions of the design space, right? And in terms of the use of machine learning, we can think about this as the theoretical principle of how to use active machine learning for optimizing search, right? So think about, you have a large search space, and you are increasingly, as you do more and more design space exploration, you're kind of trying to prune down the design space into small, more promising designs, right? So that's what search optimization mean in this context. So one canonical example here is what is called a stage algorithm for local search procedures. So what a local search procedure does is, you have a particular design, and you design some kind of a successor function, like how you explore the neighborhood, right? And the neighborhood is designed by, let's say, you remove one link and you place that link in another, between two another nodes, right? And you can do that in many ways, right? And these are all basically would form your neighbors. And once you know this neighborhood, all you can do is, well, I can just basically do a hill climbing using my cost function until I hit a local optima, right? But the main issue with basically this particular algorithm is that what kind of local optimas that you would get would depend on where you start your search, right? If you start your search in very bad starting states, then you might not get into very good local optima, right? Or close to global optima. So the key question really is that, can we use machine learning to figure out what are good starting states, right? So here is the iterative algorithm. So what it does is, in each iteration, it selects the starting state, right? And this green is the starting state, and it looks at all the neighborhoods, right? And then it keeps taking a hill climbing as a function of the cost function, and until it hits a local optima. And then the new training example is basically that, okay, if you start at any state on this trajectory, you would basically get this local optima, okay? And you feed this new training example and all the past training data to a regression learner, and it would learn that, okay, if I start from any of these states, I would end up with this local optima. And now I have an evaluation function that can estimate how good a local optima would be if I start my search at a particular state, right? So in some sense, if I already know that if I start my search at a particular state, and the cost function of the local optima would be very high, then I will probably not do local search from that starting point, okay? So once I have this evaluation function, then all I do is I try to find those starting states that would result in high local optima. So for example, this is what the point, and then I do the local search from the selected starting state, and it's an iterative process. As a function of new training data, my evaluation function improves. So let's look at each of these steps, right? So I have my evaluation function, which is basically a regression function. So it could be a simple linear model, it could be a simple neural network, or it could be a regression tree. And then I will evaluate, I start my search from here, and then I look at all my neighbors and see which of them has more promising evaluation function value, right? And I keep doing the local search until I hit a local optima. And now at this point, basically, I'm saying that this is the best starting state given my current knowledge. And then from there, I do my local search, which is the communication cost. And at each iteration, I would basically look at all my neighbors and pick the one that has the lowest cost and keep doing that. And I get the local optima, which is 0.89. So now the training data generation, right? So for you look at the trajectory, this highlighted trajectory in terms of the red states, and you look at every state that I am in, what is my evaluation function predicting? And if my evaluation function is not able to predict that I will only be end up with a local optima of cost 0.89, then I have made a mistake and I want to correct it. And the only way I can correct it is by adding a training example. So for any of these nodes where the evaluation function doesn't match 0.89, I would create a regression example. So the input is the features of this particular node, right? So you can have the link locations and the core locations or some aggregate hand designed features. And then the output is 0.89. So what you are saying is that if I start my local search at any of these red states, I would end up with 0.89. That's the knowledge that you are trying to teach. And then you give this aggregate training data to a black box regression learner. It could be a linear regressor, it could be a deep neural network, or it could be a regression tree, and you get an improved evaluation function because you have new training data from your previous search. So let's look at some experimental results. We are talking about a small world design space, a 3D mini-core system with 64 cores, with 4 dice, and we are using Splash 2 and Parsec benchmark. And the way we will evaluate the optimization methodologies is as a function of the amount of time that you are searching, what is the cost of the best design that we have explored so far, okay? And then the second evaluation metric is how fast these algorithms converge to near optimal solutions. So here on x-axis, I have time in minutes, and on y-axis, I have the cost of the best design that we have figured out. And as you can see, compared to the simulated annealing and the genetic algorithm, the stage algorithm quickly reaches very, very good designs and converges in a very short amount of time. So stage has better anytime performance, which means that at any point of time, it has better solutions compared to its baselines. And it also converges fairly fast. For example, these methods took probably even more than 50 minutes or 60 minutes, whereas here already within 5 minutes, the stage algorithm has converged. So now the thing is that this difference might not look as big, but when you go to bigger system sizes, for example, 64 cores versus 128 and 256, the speed up factor is kind of huge when you apply this stage algorithm, okay? And it also is very beneficial when you look at design space size increase due to the integration technology like monolithic 3D because of the design of both cores and routers spanning multiple tiers. So now, so far, whatever I have talked about is, okay, you have only a single objective that you are trying to optimize. But what if I have multiple analytical objectives for performance, power, thermal and reliability, and so on? So of course, there are multi-objective optimization algorithms, analogs of simulated annealing and the GA, which are AMOSA and NSGA2. and they also suffer from a similar scalability and accuracy challenges. So the researchers have extended stage algorithm to handle these multiple objectives. In fact, this algorithm was developed by Biresh. It can be seen as a generalization of the stage algorithm for multiple objectives. So when you have a single objective, you know that there is basically one point with an optima. But when you have multiple objectives, there is not a single optima, right? So the overall solution of a multi-objective problem is what is called a Pareto set, which means that these are the designs that optimally trade off these objectives. And after you are done with the optimization, the hardware designer can decide, okay, what is the most appropriate trade-off that an application requires, and you select that particular design. Okay, and you would do that by performing simulations over this Pareto set. So again, the move stage has a similar flavor as the stage algorithm, and the only thing is that in the previous case, we had a single function to kind of evaluate a design. But now, when the performance of the local search, we would be evaluating using Pareto hypervolume, right? So which means that given any set of solution, a Pareto set, I can measure how good that is, right? And our goal is we want to do local search from those starting states that would give very high quality Pareto set solutions. Okay, so it's pretty much the stage algorithm, but the key difference is that you have to take into factor into account that we are looking at a multi-objective optimization problem, and we need to adapt the algorithm accordingly. So here I'm showing you a few examples. So we are looking at a 3D heterogeneous Manycore design. So we have a 36 tile system with 4 CPUs, 8 LLCs, and 24 GPUs. So this is a 3x3x4 configuration, right? And then we use a GPU watch power profiler and 3D IC thermal simulator while performing the design space exploration. So here I'm showing you 3 graphs. The first graph is similar to the anytime curve that we have seen so far. As a function of the amount of time, we are kind of measuring what is the quality of the Pareto set that we have figured out so far. And the first thing that I want to show you is that the move stage algorithm converges. It has a better anytime performance, and it also converges in 11 hours. Whereas the MOSA algorithm doesn't even converge even after 95 hours, and there is still quite a bit of gap in terms of the quality of the solutions. So in this particular example, it's about 9x speed up. The second curve I'm trying to show is that over time, as we have explored more and more designs, the error rate of the evaluation function goes to almost 0, which basically means that we are learning very good knowledge about our design space exploration. And the last thing I wanted to talk about is that, okay, well, there is basically difference between the quality of solutions of the Pareto set, but how does that turn into in the context of hardware design objectives? So here we are showing normalized temperature delay product because we are looking at a 3D system, so we care about temperature and also energy delay product. So as you can see, there is quite a bit of gap between the solutions that MoveStage produces and the solutions produced by Amosa. And here, we are showing basically a bunch of, applications for which we are kind of trying to design the heterogeneous Manycore with 2 objectives, 3 objectives, and 4 objectives. And as you can see, that as the number of objectives increases, the complexity of the problem increases, and the speed up factor for move stage grows. And the other thing is that even if you give a lot of time to Amosa, it never uncovers the kind of solutions that move stage produces, especially for 3 and 4 objectives and potentially for large design spaces like monolithic 3D. So it's not all solved. There are lots of open challenges. I mean, like I mentioned to you, especially if you talk about you know M3D based designs, heterogeneous designs, the routers extend over multiple tiers, and the MIVs are more energy efficient than TSVs. But it also brings a lot of challenges because now the design space is exponentially bigger when compared to a corresponding, TSV based system. So that's the first part of the machine learning algorithms. The second part I'm going to talk about is Bayesian optimization for when we have to do expensive cycle accurate simulations to evaluate designs, right? So the overall workflow is that we have used the hardware designer's knowledge to design analytical objectives, and we have solved using machine learning algorithms these multi-objective optimization problems to narrow down the design space to a small set of promising designs. And among this promising set of designs, we want to search for the best design using cycle accurate simulations, right? Of course, even though we have narrowed down the search space to a small set of designs, because the simulations, the cycle accurate simulations are so slow, we cannot do an exhaustive search over this reduced design space, right? And we need new tools, and that's why we are going to talk about Bayesian optimization. So the big picture of Bayesian optimization framework is that you have a design space or a reduced design space, and what you do is that it's an iterative algorithm. You build what are called statistical models, right? So these models, based on the past training data, they will be able to predict what the design evaluations are going to be for unknown designs, but they can also quantify their uncertainty. Okay, so they will tell you what they know and what they don't know. Okay, and you have to factor that into account when you are selecting your next design for simulation. Okay, so in each iteration you select a design and then you give it to the simulator, and then the design and the corresponding quality metrics goes to training data, and you use the training data to update your statistical models, and the statistical models are cheap to evaluate when compared to the simulation. That's the key idea here. Okay, and you iterate the process, and the overall goal, it's basically similar to the machine active learning principle, where in each iteration you are basically thinking about which problem I want it to be solved from the expert, and in this case it's the cycle accurate simulator. So the high level overview is that we have a statistical model F. So I'm going to talk about this whole framework in the context of single objective, but you can have an easily the same analog for multi-objective problems as well. So in each iteration, what you do is you have what is called an acquisition function. Basically, you can think about this as a utility function. And what it does is, it basically, based on the current statistical model, it tries to assign some utility score that tells which designs are more useful to get the training data so that I would reach my goal of finding the best designs as quickly as possible. Okay. So in each iteration, you select the design with the highest utility or the acquisition function value. And then you run the simulation with the selected design, compute its quality, and then based on the new training example, you update the statistical model and the best uncovered design so far. So here I'm showing you a toy example, right, for a one-dimensional continuous function. So you have x, right, and then there is a function f of x you're trying to optimize, which you don't know, and it's a black box because you have to think about f of x as your simulator, right? The only thing that you can do is that if you select the point x, you can actually get f of x. Okay, so you don't know the form of the f of x, nor you can take derivatives to do some kind of a gradient search over it. Okay, so our current statistical model, so we have basically two training examples so far, so this point and this point, and as you can see here, I know exactly, so this is the true function, the red colored, right, but I don't know that. I only know the value of the functions at the points that I have evaluated, which are these two black points. And I want you to look at two things. One, this function that we are kind of the surrogate statistical model that we are building. So based on these two training examples, we have built a statistical model. And for all the unknown values of x, right, I have a prediction for f of x, but I also have some uncertainty or variance, right? And the key thing that you want to think about is as you move away from the points that you have evaluated, your uncertainty grows. Okay, whereas if you are closer to the point that you have already evaluated, you are fairly confident about your prediction, right? Which kind of intuitively makes sense. So the utility function, it has some form, and in each point, each iteration, what you do is that you select the point that has the highest utility function, in this case, the blue point, and then you ask the f of x, which is the red curve, to give you the value of f of x. Okay, so I got the point. Now my function, the statistical model kind of changed. Again, I repeat, I select the point that has the highest utility and do the evaluation using the red colored curve. Okay, so now my statistical model again changed, and my utility function also changed. I select the point that has the highest utility here, right? And then I evaluate. So as you can see, as I get more and more designs, my function, the black colored line, is becoming closer to the red colored point, and my uncertainties are also kind of, going down. Now, there are two things that I want you to notice. One is we are not trying to exactly approximate this red curve. All we care about is how can we approximate the function such that we have to find the optima of this red curve. Okay, so our goal is not to mimic the behavior of the red curve, whereas we want to do some mimicking sufficient enough to find the optima of the red curve. So yeah, we keep repeating the process, and as you can see, already this part of the curve, it's fairly known. We are fairly confident about all the design evaluations in this particular region, and so on and so forth. Okay. So there are three key elements in Bayesian optimization. One is called surrogate statistical model. So the key thing is that it should be cheap to evaluate unknown designs so that you can actually make predictions about what the evaluations of those designs will be. And then the second thing that we want from the statistical model is that it should be able to quantify the uncertainty of its prediction. So for example, in this particular statistical model, the variance gives you the uncertainty. And the acquisition function assigns a utility score to each candidate design using the mean and the variance obtained from the statistical model to basically assign a score. That higher the score, it's more useful to get this design evaluation that will allow us to reach the best design quickly. And then the optimizer, it tries to select a design that has the highest acquisition function value or the utility to perform the design evaluation, and then you repeat the process. Okay. So for surrogate statistical model, there are three choices. One is called Bayesian regression model. So all you are doing is that you have a linear regressor, like you have weights and features, and w dot x is a linear function that would assign basically a regression value. Bayesian regressor essentially has a distribution of weights. Essentially, you have a mean and you have a covariance. So which means that you can sample functions from the Bayesian regression model. The next is Gaussian process model. It's a non-parametric model, and it is defined based on a kernel over designs. Okay, so once you specify a kernel, automatically you have a non-parametric model, which is kind of really good. So it's very popular, but I'm not going to go into the details. The other off-the-shelf choice is random forest, right? So your random forest is nothing but a bunch of regression trees, and the mean is the empirical mean of the prediction from all the trees. So you go to each tree, make the prediction, you take the average, and you take the sample variance also from the predictions, right? So very simple to implement. It may not be as principled in terms of quantifying the uncertainty, but it often works well. And if you want uncertainty, there are variants called Mondrian forests, and that might work very well. And these are the ones that are used in a popular software called ESWEEK. For acquisition functions, you have choices like expected improvement, upper confidence bounds. I'm not going to go into too much details of these, but essentially they look at, your uncertainty and your predictions to decide, which points are more promising to evaluate that will allow you to go to the best design. And for optimizers, in the context of continuous spaces, you can actually do some kind of gradient descent with random restarts, or you can use a second order method like LBFGS, or people use what is called a divided rectangles. So essentially you divide the continuous space into multiple rectangles, and then you search these rectangles in a divide and conquer manner. So with that, we are probably close to the educational tutorial. The first take-home message I would give is machine learning is not a magic wand. Okay, so if you think that machine learning is a magic that you just say, you tell the design optimization problem, it will solve, that's not going to happen. There is still quite a bit of gap between in terms of the automation tools before machine learning can be used off the shelf. Okay. So, and off-the-shelf solutions, sometimes they are somewhat inefficient for design automation problems. And what you need to know is you need to learn about the machine learning technology, the basics, foundations, and then you have to also bring in your hardware designer's knowledge. And you need to think about what is the best way for me to formulate this problem that will allow me to use machine learning in a more efficient manner. And oftentimes, some of these problem formulations has some nice structure within it, right? So structure is kind of an abstract word. The computer science people keep using that, but when you see it, right? So sometimes you see that there is a clever approximation that you can do, and without any loss of information, right? And that would allow you to get a very tractable algorithm. And oftentimes, people ignore domain knowledge and think that the machine learning algorithms and a whole bunch of training data would actually solve my problem. In fact, that's not true. Even within machine learning field, people are moving to the other direction because you cannot get as much training data as you want. So you want to use domain knowledge, the physics of the problem, and so on and so forth to design efficient machine learning solutions. So you always want to use domain knowledge from the designers, because hardware designers have been designing this for several decades now, and they have lots and lots of knowledge that they bring to the table. So you don't want to throw it away. The other thing that I want to say is that you want to build analytical models using your domain knowledge and the workload analysis that you have done, and also these statistical models from the expensive design simulations, and use both of them to do intelligent design space exploration. Okay, so you combine domain knowledge, physical knowledge, and the knowledge from the workload and the knowledge from the design evaluations to do intelligent design space exploration. So the second take-home message that I want to give is that machine learning and big data analytics have benefited hugely from EDA community's work. In fact, all the successes that we are seeing for deep learning, right, over the last 7 or 8 years, they wouldn't have been possible without the excellent contributions made by the EDA and the computer architecture community, especially these GPUs and TPUs. Okay. And EDA community, like Biresh has mentioned, it has started using machine learning and data analytics to improve the design automation tools. And we are increasingly seeing more and more work being done, but we think there is a lot more work that needs to be done before the design automation tools reach to a level of maturity that they would need minimal help from a hardware designer. And the last point is that there is a nice symbiotic relationship between machine learning and electronic design automation, and especially in the context of mini-core design, both machine learning and the mini-core design experts, they bring some unique knowledge, and you want to work together to actually solve problems at the intersection of these two disciplines. There is this paper which is a little bit old now, but it still has some very nice perspectives about this particular view. So with that, Biresh, I would like to thank everybody who sticked around for this educational tutorial, and hopefully you found it useful. So with that, we have about 10 minutes or so for questions. So we would be happy to take questions. Thank you. Yeah, so Shail has a question. He basically is asking how to incorporate domain knowledge into Bayesian optimization. There are many ways to do that, Shail. So one way to do that is designing good kernels. Okay. So for example, you kind of tell the machine learning algorithm there are too many core designs, and when they look very very similar in terms of their overall design evaluations. If you have a way to kind of define that and tell basically the algorithm, that's one way to kind of incorporate domain knowledge. Other ways to incorporate domain knowledge is, let's say, I talked about, you have these constraints that, for example, the network should be connected so that every core can communicate with another core. So if you don't specify that knowledge, then the Bayesian optimization algorithm has to figure out itself, because it might come up with designs where the network is not connected. Similarly, there is this other knowledge that I mentioned about fat routers, right? So if you don't tell that fat routers are bad from a physical perspective, then Bayesian optimization might even search for those designs where the routers are fat. So specifying some of them, either in terms of inputs that go into the Bayesian optimization algorithm, like kernel design, or you specify declarative constraints that specify, okay, there are some parts of the designs that are really, really bad from a physical perspective, and you should not even be touching any parts of those design space. Does that answer your question, Shail? Okay, good. Any more questions? We still have time. Okay, so because there are no more questions, I would actually ask a question to the audience. How many of you are undergraduates? And how many of you are convinced that you should be working in this area to pursue graduate studies? You can type in the chat, it's fine. Or even a master student who decided, I want to pursue a PhD. Anyone else? Yeah, so 1 more minute. If you have any questions, we would be happy to answer. If not, then, after a minute, we will close the session.
Hi guys, Andreas here. Hey Jana.
Oh, hi.
How you doing?
I think we should ask you.
No, thank you for doing this. All right. Thanks for giving the lecture, much appreciated. Did everything go well?
Yeah.
Okay. Say hi. Sorry, I have my daughter with me here.
That's okay, don't worry.
No. Yeah, thank you guys for doing this, right? It's a new initiative we have, so we'll see whether it sticks, but hopefully it was useful for the audience and the students and also for you guys potentially, right?
Yeah, it's a very good initiative. I really like when Aviral and Akash described about it. I think I think that was a very, very well motivated. I think every time we think about our audience as researchers, but I think we should think about audience as undergraduate students. So we increase the EDA community beyond wherever the researchers are coming right now. Yeah, hopefully this would be a start.
Yeah, thank you. Sorry, he's making noise here. Well, hopefully to see you guys at the conference, right? You may be available there. We have the Gather Town space where you can hang out now, potentially a little bit.
Yes.
Questions, right? Also with other speakers. And thanks again for doing this, Jana and Biresh.
Thanks.
Thank you.
And hopefully we'll see each other in person anytime soon.
Sure.
Last
Yeah,
time
and
I
thanks,
think the tutorial
thanks everyone.
at some other ESWEEK, right?
Yeah.
Awesome. All righty.
Okay. Thank you, Aviral. Thank you, everybody. Yeah, thank you, Biresh.
Thanks, everyone.
You can stop the recording now.